Hello. So let's continue with the properties of orthogonal transformations. And now what we're going to do is to study them by the matrices corresponding to those transformations. And why do we care? The reason why we care is that rotation is an orthogonal transformation. And we need to have a really good expertise with dealing with rotations in computer vision. So I'm going to take you through a math lecture which is on properties of rotations. But rotations are special classes of orthogonal transformations. It turns out there are two kinds of orthogonal transformations. One are rotations and the other are reflections. But let's get to this in a second. What I'm going to do is we are going to study orthogonal transformations through their matrices. So orthogonal transformations are linear transformations and therefore they correspond to matrix multiplication. What we're going to do is to study properties of those matrices. So suppose we have a point B represented by a column vector. We have an orthogonal transformation psi which corresponds to a matrix A. So therefore psi of the point applied to the point B is really the matrix A multiplied with the column vector B. So we know that this is a orthogonal transformation and what can we say about its matrix? As an orthogonal transformation, it has some special properties. What does that imply about the matrix A? We call the matrix associated with an orthogonal transformation an orthogonal matrix. So in other words, we are going to start to study properties of orthogonal matrices. Okay, let's do that. So let's try to use the definition. Of an orthogonal transformation. So let's say we have two vectors A and B. So A dot product with B is the same as psi of A dot product with psi of B. Okay, but now what is psi of A? This is A times A, where A is the big A, is the matrix corresponding to the transformation to psi. And psi of B is A times B. Okay, so let's capture this. So we want to show that A dot B is the same as psi of A times a dot product with psi of B. So how is that going to work out? How do I compute So what's the dot product in matrix vector notation? Vector matrix notation. So let's take an example. We want to compute the dot product of two vectors A and B. And this is really the same as you take the transpose of the vector A and then you do a matrix vector multiplication with B. So suppose A was a 3 by 1 vector and B was a 3 by 1 vector. What is A transpose going to be? It's a 1 by 3 vector, and B is going to be a 3 by 1 vector, and when we do the multiplication in this way we get a 1 by 1 vector, which is just a number. So this is a standard way to get scalar products. Okay. So let's go back to our condition. The dot product of A and B must be the same as the dot product of psi A and psi B. This is by definition. Okay, so let's rewrite this. This is going to be A transpose B. Now we are thinking in terms of vector notation. Vectors. And what is psi of A going to be? This is going to be A dot product with A B. Okay. Now how do I capture this dot product? What I have to do is to take the transposed of one of these guys. So A transposed AB. And let's simplify that out. That gives me A transposed A B. Okay, let's rewrite this. Therefore, A transpose B equals A transposed So this is a relationship which is true for all choices of A and B. So just for simplicity, consider A and B in R2. So therefore there are two by one column vectors. So we can now consider A and B to be various unit vectors, various choices of basis vectors. Zero, 1 or 1, 0. So for example, we could have AB 1, 0 and BB 1, 0. So like a unit vector along the x-axis. And what we know is that A transpose B is equal to A transposed A B. Definition of orthogonal transformation. Okay, so but now we can take these particular specific examples. So if B R, then what do we get? So A transpose B will give me 1. Okay, that's what we get on the left hand side. What happens on the right hand side? On the right hand side I have 1 0 transposed. Then I have this matrix A transposed A, and let's just call this matrix C11, C12, C21, C22. And what I have done is I have defined C to be the matrix A transposed A, and here I have 1 0. Okay, so let's simplify this further. This gives me 0, sorry, it gives me 1 0 C11, C12, C21, C22, 1 0. And what is this going to give me? This essentially selects out C11. And now we know that these two relationships together tell us that C11 must be equal to 1. So let's just pause a little bit so that we are not totally lost. What I did was I had a relationship which I wanted to study the properties of A transposed A. And what I did was I picked a particular choice of the vector A and a particular choice of the vector B, and from that I showed that this matrix A transposed A, which I am calling C, has the property that C11 is equal to 1. And I can now try out different choices of A and B, which will effectively select different entries in C. And by this kind of process, we can show that C is the identity matrix 1 1 0 0, and this is of course the matrix A transposed A. Now this is really not that surprising, because if you recall my basic setup, A transpose B was A transposed times this matrix A transposed A B, and if that kind of leads one to expect that this matrix must be the identity matrix I, where I is the identity matrix 1 0 0 1. So that's what we have shown. So what we have shown is that and sometimes this is used as a definition. This is used as definition, as the definition of an orthogonal matrix. In other words, a matrix A is said to be orthogonal if it has the property that A transposed A is equal to I. Okay, so let's plug ahead. A transposed A equals I. Actually, you can say a lot from this. So I'm going to just try to derive some conclusions. First of all, this says that A transposed is equal to the inverse of the matrix A. Because the property of an inverse obviously is that A times A inverse should be equal to the identity, and here A transpose will serve as the role. So this is very nice. This means that when we want to find the inverse of an orthogonal matrix, all you do is you just transpose it. The rows become columns and vice versa, and now you have got the inverse. So this is very nice.